Now we're going to learn about kinetic energy and how it relates to the concept of work that we just learned about. So kinetic energy is the energy associated with the motion of an object. And kinetic energy has a fairly simple mathematical expression. We say that the kinetic energy usually symbolized as KE, sometimes people just write K, is 1/2 times the object's mass times its speed squared. Now there's a really important relationship between work that we just discussed and kinetic energy. This relationship is known as the WorkEnergy Theorem, or sometimes people call it the Kinetic Energy Theorem. And it says that the total work done on an object, or the net work done on an object, equals the object's change in kinetic energy. Or another way to write that is work net equals kinetic energy final minus kinetic energy initial. So let's see how this works for some applications. And the example I want to do is example 5.3 from your textbook. In this example, we'll be analyzing a car braking, a car coming to a stop. And this is something that police and forensic scientists can do to analyze collisions. So let's say that we have a car of mass 1,000 kilograms. That's initially traveling at 35 meters per second. That's somewhere around 80 miles per hour. So someone going fast freeway speed. And they need to stop. They need to reach a final speed of 0 in order to avoid colliding with someone. Let's say that the brakes on the car are able to cause a friction force on the car of 8,000 newtons. So we can ask a couple questions. First question, how far a distance does the car travel before it comes to a complete stop? Now we can use our WorkEnergy Theorem and the definition of work that we learned earlier to analyze this problem. So the WorkEnergy Theorem says that the work done on this car equals its final kinetic energy, or 1/2 mv final squared, minus the initial kinetic energy, 1/2 mv initial squared. And if we think back to our definition of work, for a friction force, the force of friction always opposes the motion. So the work done on the car F delta x cosine theta is going to be that friction force, lowercase f, times the distance traveled, this is our unknown in the problem, times cosine of 180 degrees, because friction forces point in the opposite direction of the displacement. So the force vector and the displacement vector here are in opposite directions, or 180 degrees apart, which means that this amount of work done is going to be negative. Okay, so now we can combine these two equations. Negative F delta x equals 1/2 mv final squared minus 1/2 mv initial squared. Since the car is coming to a stop, v final is 0, so that term goes away. And now we can do a little bit of algebra to solve for that displacement. Delta x equals mv initial squared over 2 times the magnitude of the friction force. And when you plug in these values that were given in the problem, we get 76.6 meters. Now that's quite a long distance. 76.6 meters is 3/4 of a football field or a soccer field, more than 3/4. So if you're traveling at a fast freeway speed and you need to stop, it's going to take you quite a long distance to accomplish that. Now let's look at part B of this example 5.3. In part B, I'll just erase this and you can rewind the video if you need to see it some more. In part B, we'll ask, how fast is the car traveling after you apply the brakes over a distance of just 30 meters? Okay, maybe you didn't see the obstacle in time that you're going to collide with, and you only have 30 meters to have your foot on the brakes. How fast will you be going after braking for less than half the distance needed to go to a complete stop? Well, we use our same method. The work on the car is the change in kinetic energy, 1/2 mv final squared minus 1/2 mv initial squared. This time v final is not going to be 0, so we have to leave that in. We do a little algebra. 2 times the work over the mass equals V final squared minus V initial squared, and we find that V final is square root V initial squared plus 2 times the work over the mass. That work has the same formula as before. It is the friction force times that distance traveled times cosine 180, because friction force is always opposite to the displacement. So we put a negative sign there. And we'll use our 30 meters for delta x this time. And when you plug in those values, you find a speed of 27.3 meters per second, which is still like freeway speed. It's still 60 miles per hour or something. So with just 30 meters of warning to step on the brakes, you're still going to be traveling at a catastrophic speed when you collide with this object. So the moral of this example is that you need a lot of distance to come to a complete stop in a fast-moving car. And the other moral of this example is that we now are starting to have some techniques where we can use energy concepts to analyze some problems. And we'll be developing these energy concepts for a broader array of problems as we go through Unit 6.